Hello, my name is Fatih Furkan Erkeç, and this is Practice Lab Deep Learning for Content-Based Filtering. We will implement content-based filtering using neural network build recommender system movies. Let's import the package. The movie ratings dataset is derived from the MovieLens ML latest small dataset. The original dataset has roughly 9,000 movies rated by 600 users with ratings on scale of 0.5 to 5. And let's run this cell. We see the title, average rating, number of rating, movie ID, and genre of the movie. By genre, action, adventure, animation, children, comedy, crime, documentary, drama, fantasy, horror, mystery, romance, sci-fi, and thriller. We have this much money movie and average rating of the genre in here and ratings per genre in here. Content-based filtering with a neural network. In collaborative filtering lab, we created two vectors, user vector and item movie vector, whose dot product would predict a rating. The vectors were derived solely from the ratings. Content-based filtering also generates a user and movie feature vector, but recognize there may be other information available about the user and or movie that may improve the prediction. The additional information is provided to a neural network, which then generates the user and movie vector as shown below. Training data. The movie content provided to the network is a combination of the original data and some engineered features. Recall the feature engineering discussion and lab from the course 1, week 2, lab 2, lab 4. The original features are the year of the movie was released and the movie's genre presented as a one hot vector. There are 14 genres. The engineered feature is an average rating derived from the user rating. The user content is composed of engineered features. A per genre average rating is computed per user. Additionally, a user ID, rating count, and rating average are available but not included in the training or prediction content. They are carried with the dataset because they are usually useful in interpreting data. The training set consists all of the ratings made by the user in the dataset. Some of ratings are repeated to boost the number of training examples of underrepresented genres. The training set is split into two arrays with same number of entries, a user array and a movie item array. Below, let's display some of the data. And let's look at some of the data: user training, user features, UVS and U_S and X count. Some of the user and item features are not used in training in the table above. The features in presets, such as the user ID, rating count, rating AU, are not included when model is trained and used. Above you can see the per genre rating average for user 2. 0 entries are genres which the user had not rated. The user vector is the same for all movies rated by user. In this table we look at the first few entries of the movie and item array. Above the movie array contains the year the film was released, the average rating and indicator for each potential genre. The indicator is one of the each genre that applies to the movie. The movie ID is not used in training but is useful when interpreting the data. The target Y is the movie rating given by the user. Above we can see that movie 6874 is an action crime thriller movie released in 2003. User 2 rates action movies as 3.9 on average. Movie Lens users gave the movie an average rating of 4. Y is 4 indicating user 2 rated movie 6874 as a 4 as well. A single training example consists of a row from both the user and item arrays and a rating from YTrain, preparing the training data. Okay, let's prepare the training data in here. To allow us to evaluate the results, we will split the data into training test and test set as was discussed in course 2. Let's do it. The scaled shuffled data now has a mean of 0. And neural network content-based filtering. And here's the our exercise 1. We use Keras sequential model in here, and let's write it down. Here, Keras layers and times 256 and activation ReLU. And let's copy that. Now 128 and num outputs. We'll do same here. Actually, let's copy that. Let's run it. And it works fine. Let's test it. All tests passed. We will use mean squared error loss and ADAM optimizer. Let's run these cells. Now let's evaluate the model to determine loss on the dataset. The loss is 0.0813 blah blah. It is comparable to the training loss, indicating the model has not substantially overfit the training data. Whereas we will use model to make predictions in a number of circumstances. First, we will create a new user and have the model suggest movies for that user. After we tried this on example user content, we can change the user content to match our own preference to see what the model will suggest. Note that ratings are between 0.5 and 5.0, inclusive in half-step increments. Let's run it. The new user enjoys movies from adventure fantasy genres. Let's find the top rated movies for the new user. Below, we will use a set of movie item vectors named item underscore vex that have a vector for each movie in the training test set. This is matched with the new user vector above, and the scaled vectors are used to predict ratings for all the movies. Let's run it. Here's movie ID, average rating, title of the movie, and genres. Predictions for existing user. Let's look at the predictions for user 2. One of the user in the dataset. We can compare the predicted rating with the model's ratings. And the model predictions is generally within one of the actual rating, though it's not a very accurate predictor of how a user rates specific movies. This is especially true if the user rating is significantly different than the user genre average. You can vary the user ID above to try different users. Not all user IDs were used in the training set. Finding similar items. The neural network above produces two feature vectors. A user feature vector VU and a movie feature vector VM. These are 32 entry vectors whose values are difficult to interpret. However, similar items will have similar vectors. This information can be used to make recommendations. For example, if a user has rated Toy Story 3 highly, one could recommend similar movies by selecting movies with similar movie feature vectors. A similar measure is square distance between the two vectors. This is the function. And exercise 2, we write a function compute the square distance. Okay, let's code that. Start with d equals to 0 and for I in range len a of the a d increment equal to ai minus bi squared, and that's it. Let's run it, and let's run that cell to test it, and it works fine. It's working fine. And a matrix of distance between movies can be computed once when the model is trained and then reversed for no recommendations without training. The first step once a model is trained is to obtain the movie feature vector VM for each of the movies. To do this, we will use the trained item underscore nm and build a small model to allow us to turn the movie vectors through it to generate VM. Once you have a movie model, you can create a set of movie feature vectors by using the model or predicting using a set of item movie vectors as input. Item underscore vex is a set of all of the movie vectors. It must be scaled to use with the trained model. The results of the prediction is a 32 entry feature vector for each movie. Let's now compute a matrix of scarf distance between each movie feature vector and all the other movie feature vectors. We can then find the closest movie by finding the minimum along each row. We'll make use of NumPy masked arrays to avoid selecting the same movie. The masked values along the diagonal won't be included in the computation. Let's run it. The results show the model will generally suggest a movie with similar genres. It will list the movies now. It takes some time. Eventually, yes, we can see the movies and the genres listed in here. So that's it for that assignment. Thank you for watching.